All right, section 6.3, we're looking at parametric equations and motion. We've seen parametric equations before, and we had defined it as the graph of the ordered pairs x, y, where x can be written as a function of t, and y can be written as a separate function of t. So x is f of t and y is g of t. Our functions defined on the interval I of t values, and that's called a parametric curve. The equations are parametric equations for the curve, and the variable t is the parameter, where I is the parameter interval. All right, now for example 1, we want to graph this function or this parametric relation on the given intervals. So when x is t squared minus 2 and y is 3t, now we've seen graphing functions on our calculator. Let's look at how to graph parametric relations. So when you're looking at your calculator, you're going to go into mode, and now instead of functions, we're going to go down and change it to par or parametric and hit enter, so that when you go into your y equals, it'll give you x and y in terms of t. So our x of t is t squared minus 2, so t squared minus 2. And our y in terms of t is going to be 3t. Okay, now part A, we're looking where t is negative 3 to 1. So what we're going to do is we're going into window, and we're going to say that our minimum is negative 3 and our maximum is 1. And then when we graph that, you'll end up with this curve. So A is a curve that looks like this. Sorry, with endpoints, because we're only looking from negative 3 to 1. B, we're going to do the same equations, but we're looking from negative 2 to 3. So we go back into our window, and we say our minimum is now negative 2, and our maximum is 3. So we're looking from negative 2 to 3. When we hit graph, now we have a curve that looks a little bit different. Something like this. And that still has endpoints. Okay, and now we're looking at part C, which is from negative 3 to 3. So when we go into our window, we want our minimum to be negative 3, leaving our maximum at 3. And when you hit graph, you can see it looks kind of like a sideways parabola. So C looks like this. Another way that we can find out the shape of a parametric function or relation is to look at if we solved it for something that we're more familiar with, so y in terms of x. And the way we would do that is we would find the values of t to substitute. So for example, if I wanted to use the first equation as my equation for substitution, I would say since x equals 1 minus 2t plus 2t on both sides, 2t plus x equals 1, subtract x on both sides, so that 2t equals 1 minus x, and divide by 2. Then I can find a value of t to substitute, 1 minus x over 2. And I'm going to substitute that into my other equation, which is y equals 2 minus t, so 1 minus x over 2. And then solving that for y, I would find that y equals 2 minus 1/2, distributing the negative, so plus x over 2. Y equals x over 2. 2 minus 1/2 is plus 3/2, which I could also write as y equals 1/2 x plus 3/2. And this is much clearer because we're more familiar with it, that our graph would be in the shape of a line. Okay, if you had decided instead of solving from the first equation for t, if you solved the second equation for t, you would end up with the same line. So we would say that y equals 2 minus t plus t plus t, y plus t equals 2 minus y t equals 2 minus y. Substituting that into the other equation, x equals 1 minus 2 times 2 minus y, which is 1 minus 4 plus 2y. Again, we're solving for y because that's the way we're used to seeing our functions. Functions are y in terms of x. So I have negative 3 plus 2y equals x plus 3. 2y equals x plus 3 divided by 2. And y equals 1/2 x plus 3/2. So they match. Sorry, I went off the screen there. Y equals 1/2 x plus 3/2. Okay, and then if I'm graphing this, I would say my y-intercept is 3/2 or 1.5. Rise is 1 over 2 or 1/2 over 1. So this would be my line. I'm going to leave example 3 for you to do using the same process as example 2, and then compare your answer to example 1 and see if the graphs from example 1 make sense with your answer. All right, in example 4, we want to eliminate the parameter, and now we're working with the functions of sine and cosine. So our favorite identity that involves sine and cosine is that sine squared of t plus cosine squared of t equals 1. In order to use this identity, we have to get sine and cosine. So we have sine here, but to get cosine, we would have to do x divided by 2 equals cosine of t. So using this new equation, we can say that sine of t squared plus cosine of t squared equals 1. Sine of t is y, so y squared plus cosine of t is x divided by 2. So x over 2 squared equals 1. So we have that y squared plus x squared over 4 equals 1. Now if you recognize this equation has the graph of an ellipse, so what our graph would look like would be like this. If you don't recognize that as an ellipse, that's fine. What you would do then is say y squared equals 1 minus x squared over 4. And then when we take the square root of both sides, remember we have the plus or minus. So you have y equals the square root of 1 minus x squared over 4 and negative square root of 1 minus x squared over 4. And you can put those two equations into your calculator and you will have this graph. But essentially, what we end up with is that we have the equation of an ellipse. In example 5, we're looking for the parametrization of the line through these 2 points. So let's see what that looks like. If I draw those 2 points on a coordinate plane, let's see, we have negative 2, 3, and 3, 6. So this is the line that we're looking for. And the trick here is to use vectors. And if I draw in, here's A and B, my vector from the origin to A. If I wanted to use vector addition, I could find this point P, which is xy on the line. And I can say that head to tail rule O to A plus A to P would give me this vector here, OP. Okay, so if I say my line XY equals OA plus AP, and then I can say that AP is some scalar times my vector AB, right? So AB is this vector here. AP is just the same line but a different size. So I can rewrite this as OA plus some constant times AB. Now I know that OA is the vector -2, 3 from here. And to find the vector from A to B, that would be a vector subtraction. So plus t times, starting from B, subtracting A. So 3 minus -2, comma 6 minus 3. So this is -2, 3 plus t times 3 minus a -2 is 5, 6 minus 3 is 3. So then I get -2, 3 plus 5t, 3t, which I can then write as 5t minus 2, 3t plus 3. Now this is going to give me my x, and this will give me my y. So I can say that x equals 5t minus 2, and y equals 3t plus 3. And the trick was finding that random point P on the line and then rewriting that in terms of the A and B that I know. In example 6, we're looking at a segment of the line from example 5, specifically the segment between A and B. So what that means is that, remember when we created our point P, here was our A and B. When we made our point P, we said that AP equals T times AB. Now, if we are only looking to be within the segment from A to B, we want that T to be greater than 0, because that will give us, if it equals 0, it would go from A to A. If it was negative, it would go to this side of A. And if it's, so we want it to be 0 all the way up to, if it's 1, then we've reached B. If it's greater than 1, then we've gone beyond B. So we want our T to be from 0 to 1, where our x and y are the same as from example 5. So our x is 5t minus 2, and our y is 3t plus 3. So this gives us just the segment between A and B. The second part of example 7 got cut off, so go ahead and pause the video and copy down the rest of the problem. The way we are going to solve example 7 is using our graphing calculator. So in order to graph Gary's position over time, we are going to let y equal the time and let x equal Gary's position. So in your graphing calculator, you're going to go to y equals. For x, you're going to put in the equation that was given. So negative 0.1 times t cubed minus 20t squared plus 110t minus 85, and parentheses. And then for y, we're just going to put t. And that way we have our equation looking at Gary's position with respect to time. Okay, now when we graph it, it will look like this. What we need to do is we need to look at our window from 0 to 12. Okay, that looks better. So notice how it goes off my window a little bit. I'm going to go ahead and go zoom, and I'm going to go down to where it says fit. Oh, there it is. And that way it will fit my whole graph into my window for me. There we go. So this is the Gary's position with respect to time. So as you can see, he was walking, and then he turned around and started walking the other way, and then he turned around and started walking the first direction again. So what I want to know is I want to know where, at what time this turn and this turn happened, right? We're looking for the times. So how we can use that is using the trace feature and kind of tracing along the line. So we're looking at our t values. So I would like to trace along the line, increasing my t value until I get to the first curve. So the first curve here is when t is about 3.9. So I'll say t equals 3.9 is my first curve, and then my second curve, as I trace along, is when t is here about 9.5. So t equals 9.5, and that will be the answer. All right, looking at example 8, a distress flare is launched from a ship's deck 75 feet above the water with an initial vertical velocity of 76 feet per second. Graph the flare's height against time, give the height of the flare above the water at each time, and simulate the flare's motion for each length of time. Okay, so the first thing to recognize here is that we're looking at a velocity with respect to, or a position and velocity. So recall that the height of an object can be written, or the position of an object can be calculated by 1/2 a t squared plus v naught t plus y naught. When we've seen this before, we were calling acceleration gravity. So you might remember this from the 1/2 g times t squared plus v naught t plus y naught, or s naught for position. It's the same equation that we have been using before. Okay, in this case, we're letting y be our height and x be our time. Okay, since we're looking at acceleration due to gravity, we can say that a equals -32 feet per second squared. So when we substitute into this equation, our initial position, our y naught, is 75 feet, and our v naught, our initial velocity, is 76 feet per second. So we get y equals 1/2 times -32 t squared plus 76t, plus 75. And when we graph that, we'll get to see our height. So for part A, we're looking at when t is 1, what is our y value? So we can say h of 1 equals -16 times 1 squared plus 76 times 1 plus 75, which is -16 plus 76 plus 75, which gives us 135 feet. Similarly, for part B, we're looking at h of 2. When you calculate that, you'll get 163 feet. Part C, we're looking at h of 4, which gives us 123 feet. And part D, h of 5, gives us 55 feet. All right, so it asks for the flare's height against time. That's this equation right here. The height of the flare above the water at each time is given by each of these values, and also to simulate the motion for each length of time. So if we're graphing this per unit time, we start at the boat's deck. So this is already at 75 feet. You can think of this as being like the boat on the water, and we're launching a distress flare, and it goes up and out. Okay, where we have, this would be our 0, or when the flare hits the water, and this is our maximum height, which is the vertex of our parabola. All right, looking at the next page, if we're talking about projectile motion, we can represent that as a vector. So suppose the projectile is thrown from a point y0 feet above the ground level with an initial velocity represented by the vector v equals the vector v0 cosine of theta comma, v naught sine of theta. Now remember that subscript naught means initial. So we're taking our vector of velocity is our initial velocity times the cosine of theta as our x value, and our initial velocity times the sine of theta as our y value. Okay, the path of the object is modeled by the parametric equations where x equals t times v naught cosine of theta and y equals negative 16 t squared plus v naught sine of theta times t plus y naught. All right, let's look at an application of this. In example 9, Kevin hits a baseball at 3 feet above the ground with an initial speed of 150 feet per second at an angle of 18 degrees with the horizontal. Will the ball clear a 20-foot wall that is 400 feet away? So essentially what we're looking at is we have a baseball 3 feet from the ground, and it is being hit 18 degrees from the horizontal at 150 feet per second. And we want to know 400 feet away, we have this fence. So this is 400 feet, and the fence is 20 feet tall. Okay, this picture is not drawn to scale, but essentially, as the baseball travels, it's going to go up in an arc, and then it will start to go back down due to gravity. So what we can do is say that x equals 150 cosine of 18 degrees times time. This is from our previous equation. And that y equals negative 16t squared plus 150 times times sine of 18 times t, and then plus 3. Our initial height, this was our angle, and this is our initial velocity. All right, now we want to know, will it clear this 20-foot fence? So what we're looking for is at 400 feet away, what's the position of our ball? So if we want to set our x to 400, at 400 feet away, we have 400 equals 150 times cosine of 18 times t. Okay, notice the t is not in the argument of cosine. The t is outside of the cosine. Okay, so if we solve for t, we would have that t equals 400 divided by 150 cosine of 18, which when you put it into the calculator and make sure this is in degrees and not radians, you have approximately 2.8 seconds. Okay, now the question is, what's the height when at 2.8 seconds? So if we're looking now at our y value, we want to know our y value at 2.8 seconds. So y equals negative 16 times 2.8 squared plus 150 sine of 18 times 2.8 plus 3. Okay, and when you put that into your calculator, you will find that this is 7.35 feet, which, notice, is less than 20 feet. So no, it will not clear the fence. Okay, so what this looks like is that the ball went up, it hit its maximum and started coming back down, and it will hit the fence and not clear it. All right, looking at the next page, the last example for this section is example 10. Jane is riding on a Ferris wheel with a radius of 30 feet. The wheel is turning counterclockwise at a rate of 1 revolution every 30 seconds. Assume that the lowest point on the Ferris wheel, the 6 o'clock position, is 10 feet above the ground at that Jane is at the point 3 o'clock at the time t equals 0. Find parametric equations to model Jane's path and use them to find Jane's position 22 seconds into the ride. So I'm going to draw a picture. Here's my Ferris wheel. Okay, and the Ferris wheel is being held off the ground 10 feet. 10 feet. Okay, so the radius of the Ferris wheel, R, is 30. This is the 3 o'clock position, so this is where Jane is. I'll call it point A. And the Ferris wheel is rotating counterclockwise. So, and it's rotating at a revolution, 1 revolution per 30 seconds. Okay, so what I can use is the equations that we were just talking about, where x equals 30 cosine of theta from our radius, and y equals 30 times sine of theta. However, we also have to account that the Ferris wheel is not centered at the origin. It's centered above our x-axis, which would be the ground, right? By 10 feet for the stand, plus 30 feet for the radius. So we have to say plus 40. Okay, now we're only interested in 1 full revolution. So we're looking at theta between 0 and 2 pi, because we're only looking at 1 revolution. Okay, so what we're looking at now is we're looking at how much does the Ferris wheel turn at any given time. So 1 revolution would be our angle over time is 1 revolution, which is 2 pi every 30 seconds. Now, in order to put it into these equations, we want to solve for theta. So if I multiply both sides by t, I find that theta equals 2 pi over 30 t, which simplifying by 2 over 2, we get pi over 15 t. All right, so I'm going to scoot this down. So in order to find out when the time is 22 seconds, what our position is, we can use x equals 30 cosine of theta, which is 30 times cosine of pi over 15 times t, which is 30 cosine of pi over 15 times 22, okay, which is approximately negative 3.14. And then we'll use that y equals 40 plus 30 sine of theta, which is 40 plus 30 sine of pi over 15 times 22. And that gives us approximately 10.16. Okay, now remember both x and y are referring to our position. So we can say that Jane is 10.16 feet from the ground. Her position with respect to the y-axis from the ground, and 3.14 feet to the left, because it was a negative value, of the base. Okay, what does this look like? Well, she's a little bit more than 10 feet from the ground and she's left of the base, so she's probably somewhere right around here. We could call that point B. All right, so that's it for this section. Make sure to summarize what you learned in class and write it down in this section at the bottom.